Last week we learned about a quantity called a mole and how it can be used to make really, really big numbers smaller and easier to talk about. So we discussed this unit of measure and then we explored how we could use it to go between atoms, molecules, moles, grams, and even volume for gases. And at the end of the week, we started discussing this idea that there could be a mole to mole relationship, that if you know something about how many moles are in a compound, you can use that to find out information about other elements in the compound. So today what we're going to talk about is how to determine how much of a certain element is making up a compound, and we refer to this as percent composition. So percent composition is defined as the relative amounts of the elements in a compound expressed as a percentage or the mass percent of each element in the compound. And we refer to it as a mass percent because we use the masses to determine the percentage. So if you look at this pie chart, we have potassium at 40.3% of the compound, potassium chromate, and the chromate is making up 26.8% of the compound, and oxygen is making up 32.9% of the compound. And so even though it's K2Cr1O4, the oxygen and the potassium and the chromate are making up the compound in close to similar amounts, even though there's 4 more oxygens than there are chromates, and this is because we're actually considering the percent composition in terms of mass. So here's what that looks like. We would say that the mass percent of an element is the mass of the element divided by the mass of the compound multiplied by 100. And so to calculate a mass percent, you would need to know the mass of the element and also the mass of the compound. The mass of the element, of course, can be found on the periodic table, and the mass of the compound could also be calculated by finding the molar mass from the periodic table. So if we add up the masses of 2 potassium plus 1 chromate plus, or sorry, 1 chromium plus 4 oxygens, that gives us 194.2 grams per mole. And then since we have 2 potassiums in our compound, we're going to multiply by 2 when we insert the molar mass of potassium, and so we'll have 2 times 39.1 divided by 194.2 multiplied by 100 to make it into a percentage, and that gives us 40.30% potassium. Similarly, with chromium, we see that there's only one of them, so we're going to do 1 times the mass of chromium divided by the molar mass of potassium chromate, the compound, multiplied by 100, and we find the 26.8% mass. Finally, we have oxygen. There's 4 oxygens in this compound, so we'll insert 4 multiplied by the molar mass of oxygen, which is 16, divided by the molar mass of the compound potassium chromate, and we'll multiply by 100 again to get 32.9% as the percent composition. So let's go ahead and try an example to solve for percent composition. In this example, we want to calculate the mass percent of each element in the molecule penicillin F. Penicillin, of course, is a type of antibiotic that we use even now to treat certain types of infections. and it has a long formula, C14H20 into SO4. It's a pretty big molecule, and so we're going to figure out what percent by mass each element in this compound represents. To begin, we're going to need to calculate the molar mass of penicillin because we need to use the mass of the compound to be able to calculate the percentage of each element. So the first step is to calculate the molar mass. And if we think back to last week, we will recall that we can calculate the molar mass by using the masses on the periodic table and the number of times every element appears in the compound. So for this example, we have 14 carbons, each with a mass of 12.01 grams per mole. And we're going to add that to 20 hydrogens, each one with a molar mass of 1.01 grams per mole. We'll add that to our 2 nitrogens with a 14.01 gram per mole molar mass. And then I'll continue on the second line. We'll have 1 sulfur times its molar mass of 32 grams per mole. And finally, our 4 oxygens, each with a mass of 16 grams per mole. So if I multiply this out and add all of the components up, I wind up with a molar mass of 312.42 grams per mole. So this is the mass of my compound penicillin F. So I'll need to use that later. Now, let's just go ahead and start with carbon since it's the first element in the compound. So we're going to calculate the mass percent of each element. Starting with carbon. So what we need to do is we need to take the mass of all of the carbon in the compound and divide it by the molar mass of the compound. So there are 14 carbons in the compound and each one weighs 12.01 grams per mole. Then I'm going to go ahead and divide by the molar mass we calculated in step 1, 312.42 grams per mole. And so I have to multiply by 100% in order to turn it into a percentage. And when I do that, I find that the percentage is 53.81%. So this compound is half carbon by mass, approximately. The next element that we're going to look at is hydrogen. So let's go ahead. There's hydrogen, and we have 20 hydrogens, each with a mass of 1.01 grams per mole. We'll divide that by 312.42 grams per mole. And whoops, we have to remember to multiply by 100 to turn it into a percentage. And when we do this, we wind up with 6.453% as the percent of hydrogen in the compound. So for carbon, we have 53.81%, and for hydrogen, we have 6.43%. The elements we still need to figure out are nitrogen, sulfur, and oxygen. What I would like for you to do is pause the lecture, calculate the percentage for nitrogen, sulfur, and oxygen, and then resume the lecture to check your answers with what I got. But no, seriously, pause the lecture, like right now, and figure out the percentages. Okay, so you're back. Good job. Let's check your work. We are going to take a look at nitrogen. So if we have 2 nitrogens, each with a molar mass of 14.01, we'll multiply that out and divide by the molar mass of the compound. Multiplying by 100, you should have gotten 8.969% for nitrogen. For sulfur, we should have 10.27%, and for oxygen, you should have 20.49%. If you got something that is different than that, take a moment to go back and double check your work and see if you can figure out maybe where you went wrong. If you're really not sure, go ahead and raise your hand and ask me, and we will figure it out together. Another thing I'd like to point out about this whole calculating mass percent deal is that theoretically, if you add all of the mass percentages up, they ought to add up to 100. And in this case, if you add all of these up because of the decimals, we get 99.992%, which is just rounding inconsistencies, and that's okay. I'm okay with that. If you add them up, though, and you get like 75%, that would probably indicate to you that you had gone wrong somewhere. But if you get like 99.9%, then your percentages are accurate within rounding. So that's another way you can check your work, is to make sure that all of these guys, if you add them up, actually add to 100%. Because that's how percentages work. We can also find percent composition even if we don't know the formula of a compound, as long as we have some data on the mass of a compound. So if we had a 13.6 gram sample of a compound and it contained only magnesium and oxygen, and so we decompose it and we do some experiments and we find out that there are 5.40 grams of oxygen, then we can actually calculate the percent composition, because even though we don't have a formula, we still have a mass of the element, oxygen, and we still have a mass of the compound. And so we can use the same formula to calculate the mass percent of magnesium and oxygen in this compound. So the first thing that I'm going to calculate is, I know that the mass of the oxygen is 5.40 grams of oxygen because they've told me, but I want to find the mass of the magnesium. And the easiest way to do that is to say that if I had a 13.6 gram sample and it was only made up of oxygen and magnesium, everything that wasn't oxygen was magnesium. So I can do 13.60 grams of sample minus the amount of sample that I know is oxygen, and I can use that to find the mass of the magnesium. So there was actually 8.2 grams of magnesium in the sample. So now I have the mass of the oxygen, and I also have the mass of the magnesium. So I can calculate the percent composition of both of those components. This will look like this. We have the mass percent